Welcome to probability using the multiplication rule. So this is a continuation of the lesson from class. All right, so we have a six-sided dice. A six-sided cube is labeled with the numbers 1, 2, 2, 3, 3, and 3. Four sides are colored red, one side is white, and one side is yellow. We want to find the probability of tossing 2, then tossing 2 again. So in this problem, we're only looking at the numbers, not the colors. They don't matter in this problem. So tossing a 2 once, and you can fill in your note template, does not affect the probability of tossing a 2 again. Right? But just because you got a 2 one time on a dice, you still have all the same numbers. No number was used up, so you can just toss a 2 again, right? So those are independent events, right? So the events are independent. What you get on one roll does not affect what you get on another roll. So when we have independent events, the probability of more than one event is going to be the product of the individual probabilities. Okay, so we have two events here, tossing a 2, then tossing a 2 again. To find the probability of that occurring, we just have to take the probability of tossing a 2 and then multiply that by the probability of tossing a 2. All right, so the probability of tossing a 2, there are two sides that have 2 on them. And there are 6 sides altogether, right? It's a six-sided cube. So the probability of tossing a 2 is 2 6. The probability of tossing a 2 the second time is still 2 6. Right? Those are independent events, so the probability is not affected at all. We could reduce this to make the numbers a little smaller. 2 6 is the same as 1/3. Because I should put an equals there, times 1/3, those reduce. And 1/3 times 1/3 gives us 1/9. That's all there is to this problem, right? Let's look at another problem. Right, so if your events are independent, you just have to multiply the two probabilities, or 3 probabilities, or however many probabilities it is. Here we have 3 probabilities because it's 3 events. So the number of probabilities is going to equal the number of events. Here we have a six-sided dice, six-sided cube, is labeled with the numbers 1, 2, 2, 3, 3, 3, and then 4 sides are colored red, one side is white, one side is yellow. Same dice as before. This time we're not interested in the numbers, we're interested in the colors. So we want to toss a red, then toss white, and then yellow. One toss, again, does not affect any other toss. These are independent events. Right, so one toss does not affect any other toss, so the events are independent. You can just add that to your notes. So in this case, we're not concerned what we get on one roll has no impact on what we get on the next roll. All right, so the probability is just going to be the product of the 3 probabilities. All right, so the probability of tossing the red side, there are 4 red sides, so that's going to be 4 6. There is 1 white side, so that would be 1 6 is the probability of tossing a white. And there's 1 yellow side, so also 1 6. All right, we could reduce 4 6 reduces to 2/3, both divisible by 2. And now we can just multiply. Actually, we can reduce one more time. You could cross-reduce, right? When you're multiplying, you can reduce within a fraction, or you could cross-reduce. So I could reduce that 2 and that 6 if I want even smaller numbers. If I don't, I can just reduce afterwards. I can multiply first and then reduce. I just like to have the smaller numbers when I'm multiplying. 1 times 1 times 1 gives us 1. And now we have 3 times 3 is going to be 9. 9 times 6 is 54. All right, so that probability is 1 out of 54. All right? So we've looked at some independent events. Let's look at some dependent events. All right, so to find the probability of dependent events, you can use the conditional probability formula. The probability of event B given that event A has occurred. And we have several different tools that we're going to use for conditional probability. One is a formula one is a factor tree. Right? We're going to look at the factor tree before we look at the formula, because different problems are going to lend themselves to the factor tree, and different problems will lend itself better to a formula. Okay? We'll see that later on. So if A and B are dependent events, then the probability of A and B is going to be the probability of A times the probability of B, where given that A has already occurred. Right? Let's take a look at a dependent probability with dice again. So just because they're dice doesn't mean it's always going to be independent probabilities. Sometimes we have dependent probabilities. In this case, 2 number cubes are rolled, 1 white and 1 yellow. Explain why the events are dependent, and then find the indicated probability. The white cube shows a 6, and the sum is greater than 9. So these events are dependent, right? So if our white cube shows a 6, that's our first thing that has to happen. That's going to impact how we can have a 9, right? So the first cube showing a 6 impacts what rolls give a sum greater than 9. Okay. So it's a probability given that the first event has already occurred. All right, so now let's find this particular probability. All right, and in this case, maybe a factor tree would be a good thing to help us out. All right, so we want the probability of, so let's take a look at the first roll. The probability of A. Right, so what are the options on a normal number cube? All right, we could have a 1, we could have a 2, we could have a 3, we have a 4. Oh no, I have to do better drawing than this because I'm running out of space. Maybe if I draw it a little longer. 1, there we go. 2, I can fit it in. 3, 4, 5, and 6. So we can clearly see that the probability for A, the probability of A is getting a 6. This is, so probability of a 6. We can see there's only one 6, right? There's one choice there. Right? So that's going to be, that probability is going to be 1 6. Now we have to figure out which options are going to work with that 6. Right? So now we want a sum of greater than 9. Right? So, well, 1 won't work. And 2 won't work. And 3 won't work. Ooh. And 4 won't work, and I've again run out of space. Let's see if I can move that up just a little bit. My picture drawing leaves a little bit to be desired. There we go. But 4 will work. And 5 will work. And 6 will work. So we have 3 options, right? So given that we already have the 6 occurring, because we're told that this is the probability given this has already occurred, we have 3 options. So now our probability for the second one, the probability of greater than 9, given that we got a 6 already, I'll just put given the 6, so that just means given that the 6 has already occurred, we've got now half the choices. So our probability is going to be 1/12. Right? So here, where a factor tree might help you figure out all of your outcomes and the outcomes that work. Right? We're not interested in any other number here because it's given that 6 has already occurred. Right? So these are dependent events. All right, let's look at another very similar problem. Two number cubes are rolled, one white, one yellow. Explain why the events are dependent and then find the indicated probability. So the yellow cube shows an even number and the sum is 5. All right, explain why the events are dependent. So think about it, we want the sum to be 5. The possible ways to reach a sum of 5 are impacted by the first roll. For instance, right? So if the first roll is even, second roll's got to be odd, right? That's the only way you're going to have an odd number. So the second roll has to be odd. And add to equal 5 with the first roll. All right, so you put that in your notes. Right, there's only so many ways you can get to 5. Right, there are no negative numbers here, right? And so if I want, the sum is 5, that's an odd number. If one shows an even number, the first roll has an even number, the second roll can't be another even number because 2 evens are an even number and not going to be 5. Let's again do a factor tree here. This one really lends itself to a factor tree. And actually, I've given myself just a little bit more space on the next page, knowing how well I draw factor trees. My lines aren't very straight. So here we go. All right, so I've already drawn my possible options here and kind of showed you how the probabilities are going to work here. We already know, I didn't draw out every option. I drew out starting with the first roll. Right, so the first roll, right, we have 3 different favorable options, right? We have the 2, we have the 4, and we have the 6. Each one of them has a possibility of 1/6, right? So now we have to think of what works with each of our options, right? So with the 2, there's only one option that works, the 3, right? Because only 2 plus 3 equals 5. Right? It's got to be a sum of 5. Right? So that means this probability, so if I'm going down this tree, we have for the 2, so there's a probability of 1/6 of rolling the 2. Right? There are 6 sides. One of them shows a 2. There's a probability of 1/6 of getting the 3. There are 6 sides. Only one of them shows a 3. So the probability of a 2, then a 3, is going to be the product of those 2, right? So this is 1/6 times 1/6. When we go down when we are looking at a factor tree for probabilities, we go down the line and we multiply. So the probability of a 2 and then a 3 is going to be 1 out of 36. Right? That's the probability of getting 2, then a 3. Right? I have another possible option because it says that the first roll was even. I could have rolled a 4. That also has a probability of 1/6. There's 4. There's 6 sides. One of them is a 4. What side would it have to be to go with a 4 and add to 5? Well, it'd have to be a 1. Right? And there's only 1 and there's 6 sides. So the probability of rolling the 4 and then the 1 is going to be 1/6 times 1/6. Or 1 out of 36. All right, so both of these are good options. Now let's go down the last line here. All right, we have a 1/6 option of getting the 6. Right? There are 6 sides, one of them is a 6. But there's no option that possibly goes with the 6, right? There's no way you can roll a 6 and then have a sum of 5 because there's no negative numbers. So this is 1/6 times 0, which is 0. There's a 0 probability you rolled the 6 and got a sum of 5. That's just not possible. Now when we go down the factor tree, we add the probabilities, right? So we have one probability, the 2 and the 3, right? That has a probability of 1/36. We have a second option, the 4, then the 1. That has a probability of 1/36. And even though it doesn't work out for us, we do have a third option, right? The 6 and absolutely nothing, which has a probability of 0, right? Because there's just no way that one's going to happen. Right? So if we add those together, we get 1/36 plus 1/36, which is 2/36, which is equal to 1/18. Right? That's the probability of rolling a sum of 5, given that we've already rolled an even number. Okay? I'm going to put it also on the other page. You can either copy the factor tree, or I'll just list the options as well. Right? So you can either copy my factor tree, which is a very nice factor tree, because this time I used a line tool, or you can write it down from the other page, because I'll also put it over here. So I'm going to put a little note here. See other page for factor tree. And I'll just list them over here. All right, so our first probability, so we have our first option was the 2, right? And we could have rolled a 3 with that. So we want our first favorable outcome was the 2 times the 3, which has rolling the 2 and then rolling the 6, which has a probability of 1/6. The 3 had the probability of 1/6, and that gave us 1/36. Our second option was that we had, and actually I'll get one as a dot in between. That one doesn't really matter. I don't want you to think it's 2 times 3. It's the probability of getting the 2 times that probability of getting the 3. Our second option was the 4. And look at this, I'm even drawing the dice out for you. And then we could have gotten the 1. And that has a probability of 1/6 and 1/6. And even though it's not going to change the probability, the first dice was an even number, so we have to include the last probability, which is 1/6, and this is impossible. There's no way to get the sum of 5, so that's times 0. Probability of something that's impossible is 0, so that gave us a probability of 0. So the probability of having a sum of 5, given that that the yellow cube had the even number already. Right? So the white cube gives us the sum of 5. The yellow cube gave us the even number, is the sum of those two probabilities. Oops, and I forgot to write this one down. All right, so that would be, this one here was the even. This was the, so this one has to be, because we're trying to get the sum of 5, has to be the 1 or the 3, because that's all that will work with those even numbers, would be 1/36 plus 1/36. Right? So here a picture or a listing or a factor tree will help you figure it out. Right? It's a little harder to figure it out if you don't give yourself some kind of visual. All right? And you're just trying to multiply numbers together. All right? You want to think of your favorable options. And the best way to do that is with that factor tree. So our probability here was 2/36, which is equal to 1/18. So here we're kind of combining two different rules. The multiplication rule for getting each of the individual probabilities, and the addition rule because we had more than one favorable option. Right? We had the option of the 2/3 and the option of the 4/1. Right? Well, thanks for watching this podcast, and we'll look at more dependent probabilities later in class. Bye.